Today, we're going to look and see how we can go from our original DNA strand and our original amino acid sequence and phenotype to something that alters the DNA sequence but still produces the same phenotype, and something that alters the DNA sequence but produces a completely different phenotype. So we have our original lineup here: AGG, ACA, CCT, GCA, TTG. And we're going to say that all that combined codes for brown eyes. We're going to say brown eyes. And so we see that the amino acids are serine, cysteine, glycine, arginine, and asparagine. So that is like the amino acid sequence that makes up the phenotype, the trait. And so our first difference that we're going to look at is called a silent change, and it kind of what the name implies, you're not going to notice it. So we have our exact same DNA line here except for this one letter. We change this A to a G, and so now when we go through this entire process of translating it over to RNA, we're going to see exactly how it changes here. So our AGG, that's going to be the same. It's going to be UCC. This is going to be UG, but now this is different. Instead of an A, we're not going to have a U now in the mRNA spot. It's going to be C. It's going to be a new, different combination and ultimately a new mRNA line. Everything else will remain the same. GGA, CGU, AAC. And so now if we look what ACG converted into UGC looks like, we get cysteine, this exact same thing that we have on the top line. So now we see the exact same chain of amino acids linked together, which will produce the exact same phenotype. Even though it's not the exact same DNA line, it's not the exact same mRNA line, but it is the exact same amino acid sequence, which will result in the exact same phenotype. So that's called a silent change. The next one we're going to look at is called a missense. And so this is one that actually produces a different outcome. So we see here, everything's the exact same except now, from our original, the C is changed to a G. So we're going to look at how it changes our mRNA line. So this will remain the same, UCC. But now here, instead of getting a UGU like we got in the original line, we're going to get a UCU. And one letter difference, we've seen that it can make a difference, or in this case, or we've seen that it cannot make a difference in our silent line, or in this case, we're going to see how it can make a difference. So we're going to finish filling out the rest of our line. So now these are all ready to go and be an amino acid. So we're going to take a look at this one, which will remain the same as it goes down. It will be serine again. And now this one, it won't be cysteine. It's going to produce a completely new amino acid, which is serine. So now, instead of having serine, cysteine, we have two serines in a row, followed by the exact same. The next three remain the exact same. And now, this chain of amino acids will ultimately code for a different phenotype, which might be different from our brown eyes that we had at the beginning, might be blue eyes. Even though from this original thing, there should be no chance that this kid has blue eyes. With this mutation that we see, this missense, it will. And this is kind of why we see genetic variation from parents to kids. And so if everything goes to plan, the parents each give, one gene, and ultimately it's half and half, right? But if something goes a little bit wrong, we can see that, it might not change anything. The baby might still be the exact same, like in our silent. Or something like our missense is going to happen, where something like a physical phenotype that should not be possible from those two specific parents happens. And it ultimately creates variation that should not happen in the normal reproductive way of doing things. And so the baby will have a gene or a phenotype that is not possible from those two parents, creating something completely new.